Hello everyone, I'm here to show you how to assemble an Astable Oscillator using LM741, 3 resistors and just 1 capacitor. In order to better understand what we are going to do, we have to check some facts about LM741. Remember that this video does not explain how LM741 works. Here are some special facts about this amplifier. LM741 is an operational amplifier. In this case, we use it as an inverting amplifier. Also, at this circuit, it uses open loop gain, which is 200,000 volts per volt. Because of this gain, the difference of voltage input multiplied by gain exceeds the supply voltage, which is 30 volts peak to peak. This means that the voltage output is always in saturation, because the output of an amplifier can never exceed its supply voltage. So, in our digital oscilloscope, we are not going to see a sine output, but something that looks like a square sine. At our right, we have the circuit. As we can see, we must find the value of each component. We use these 3 useful equations. Let's make an example. If we want threshold voltage to be 1/3 of voltage output and we want frequency to be at 1 kHz with capacitance of 0.1 microfarad, what is the value of the resistance free? First, we must find the values of resistor 1 and resistor 2. In order to achieve that, we have to perform a simple voltage divider between resistors R2 and R1. Later on, we have to examine the equation of the Astable Oscillator. With this equation, we can find any of the variables of the circuit. Here is a quick look on how to assemble an Astable Oscillator. As you can see, in this assembly, I used 2 extra capacitors. Those capacitors are used in order to avoid parasitic oscillations and reduce noise. They are called voltage smoothing capacitors. Now let's see some uses of the Astable Oscillator. Blinking lights, electronic beepers, switching power supplies, function generators. Also, a stable oscillator can be called a stable multivibrator. Later on, let's examine what are the results of a digital oscilloscope in the previous example. In order to do so, we need to take a look into the amplifier equations. Operational amplifier compares voltage input 2 and voltage input 3. The voltage output always remains at 30 volts peak to peak, but we have phase change of 180 degrees. There's a problem here. At voltage output, we expect voltage output at 30 volts peak to peak, but as we are going to find out, we have about 28.4 volts peak to peak. This is because we have some losses in the amplifier. Threshold voltage is voltage input 3. Capacitor voltage is voltage input 2. Capacitor starts to charge. If capacitor's voltage exceeds threshold voltage by same sign, voltage output changes phase by 180 degrees. Then threshold voltage phase also changes by 180 degrees. Capacitor starts to discharge. Capacitor starts to charge with negative voltage. If capacitor's voltage exceeds threshold voltage by same sign, voltage output changes phase by 180 degrees. Repeat. Here are digital oscilloscope results. We can see when threshold voltage and capacitor's voltage changes. Also, we can notice that we have a square sine at voltage output instead of a sine output. because of the high open loop gain of the amplifier. Bear in mind that this amplifier has a slew rate, therefore the output signal is not exactly square. The cause of slew rate in this circuit is the rapid change of voltage between the two inputs, which causes a rapid change of voltage at the output in the order of the voltage supply. As a result, the inner capacitance of the amplifier cannot follow such a rapid transition. We can detect slew rate if we zoom in the digital oscilloscope. The conclusions are based on the effect of each component of the circuit on the period of oscillation.